Hello, good morning, students. Today, I'm going to demonstrate an experiment today for rectangular patch antenna design. A rectangular patch antenna is one of the microstrip antenna, and it is one of the interesting design that we have. So, what exactly a microstrip antenna is? I'll start with this, and then we are going to design an antenna for using microstrip antenna. Microstrip antenna or title is design and simulation of a rectangular microstrip antenna, and we can say actually patch antenna. It's also known as a patch antenna. So what is the structure is fundamentally it has a four part in the structure, and the first part is substrate. I'm drawing with the green color here. So we can say there is a cuboid shape, okay, which has a height, width, and thickness. We are going to call this as a substrate. What we are going to call substrate. So in a substrate, we'll denote it by capital S, substrate, and then its length will be SL, denotion for the length, substrate length. Substrate width is SW, and substrate height will be denoted by S capital H. It is height. So it is a fundamental part that in a microstrip antenna, we have a substrate which is of insulating material. Okay, it is an insulator. And you know, insulating material, they have the dielectric permittivity. So relative dielectric permittivity of epsilon R is there with this insulating substrate. So with this insulating substrate, we are going to now create at the bottom of this one plane, and let me draw it with a red color. It is of the same length, same weight, but the different thickness. So we can say if the length between these is as SL, and the width between them it is SW, and this is SL, substrate length and substrate width. So the ground plane which we have will denote it as ground. Ground plane as G plane. G is the subscript we are going to use, and GL the ground plane length, GW ground plane width, and GH is the ground plane height. So you know the substrate length and the ground plane length are same, is equal to SL. So we are going to use this is the same length and same width of the ground plane, and it is made up of, it is SW, and the GH is equal to MT. MT is metal thickness. Actually, what happens in a patch antenna is we have this as made up of metal. We are going to use in our case as a copper annealed copper material for this. And the patch antenna which we have, that is also of metal, and the dielectric substrate is there. So let me make another structure here. It is patch structure of a small thickness equal to the thickness of ground plane, like this, and we'll name it as P. P is for patch, S is for substrate, and G is for ground plane. Okay, so here we are going to route the third point. First is substrate, second is ground plane, and the third we are going to create is patch. Patch will have patch length, patch width, and patch height. The patch height is equal to same thickness, we mean to say. The thickness will be MT. So I think everyone is clear with the dimension now. And let me design now in a CST studio this structure. To design this structure, open your CST studio suite. It's initializing. So it is my studio suite. Go to antennas. Select my antennas, and here planar or patch antennas, time domain. Check all the units here are in the dimension, because in the previous experiment you might have changed. So it should be millimeter, and gigahertz, because we are going to design it for a 2.4 gigahertz Wi-Fi application. Frequency here, because our frequency of designing is 2.4, we'll write it here as a 2.2 gigahertz as a minimum, 2.6 gigahertz is a maximum. In between this, we are going to monitor E field, H field, and far field. Go to next. You name your project. It's a rectangular patch antenna for Wi-Fi. You can name it accordingly with register number. Here we open the project. Once it initializes, the first step is let it initialize. So you can see once we open the project, we get a boundary box and a plane here. If you roll over this, you will find the structure at the middle of this. Orientation of the plane is there. So first thing you have to do is after starting, go to modeling. Here local WCS is there on the top of the corner, local WCS. Select local WCS. Okay. Then after, go to view window, and there is a axis below this. There's a boundary box. Uncheck this. So you will get a plane here over which you are going to design your patch antenna. Is that clear? With this plane, now we are going to design the first structure. Or plane is in front of eyes. Now go to modeling, take a brick, escape, like we used to do it for cylinder. Here brick we have to select, and we are designing first is substrate. Now substrate, this brick dimension, you can see in the coordinates here. In the U direction, V direction, what we have, you can rotate in the, you can keep it in the front view, perspective view. So you can see V direction, we are going to have width. If you see the structure here, in the V direction, upside direction, if you keep it front, we have a width as this direction, L in this direction. So with this, in U minimum, you are going to write in the U direction is the length. So minus SL by 2, because we want to orient it exactly at the center. So minus SL by 2 to plus SL by 2 is your length. Width is in the V direction is going to be minus SW, because we kept SW means substrate width, SW by 2 to plus of SW by 2, and the width of this, because we want to orient it on the plane, not on the half of the plane. So if we write it as from 0 to SH, it means the height of the brick which we are going to select is this above the plane from the center. If you can see here, this plane you can see from the center is height W is starting from 0 and the plane. So we want to make it upside up to height edge. So there will be a brick ready here. Component here you can select insulating material, and we are going to use for this practical FR4 Lossy. Select it from the material library, load it. If preview, if you see, you can find it is asking for L. SL is equal to 59 mm. You can write as a length of substrate. I am writing S length. Okay. Then we are writing substrate weight. It is 76 mm already we chosen. So it is 76 mm. No need to mention mm. It is S weight, substrate weight, and the height is 1.5. It is substrate height. Okay. So with this, you can see a structure appearing here of a thickness 1.5. And now I press OK. If you can see the structure now from the plane, there is a thickness of 1.5, and we have a brick dielectric material, insulating material is ready. Now turn over this. It means in the back side, opposite side. Go to pick face. Double click here. And near the local WCS, there is a second terminal here. Go to arrow, and here write as a align with the selected face. So what we are going at the bottom, we are going to create now second component, which is ground plane. So I selected this. Now orientation has now downside. Now take a brick. We are writing as a ground plane. Ground plane and the substrate width and length are same, as you know. It is going to cover completely. Only thickness is different. So here we are going to write minus SL by 2, as we did in the previous one. Minus of SL by 2 to plus of SL by 2. V minimum is minus of SW by 2 to plus of SW by 2. And the width is 0 to MT. It means metal thickness. It is not SH. It is only difference in the ground plane. Here select the material copper, load library, and then here you can go see it is showing carbon, copper. We have to select copper annealed lossy metal. Load it. Preview. It is asking for MT. What is metal thickness? Mention here 0.03. It is metal thickness. So actually the upside patch and the ground plane both are metal copper annealed we are going to use, and the thickness will be 0.03 mm for metal thickness. So with this, if I press OK, you can see here appeared, and the ground plane yellow color shape, it shows the copper film here, and the upside is with dielectric material. Now roll over and go again to the side which is dielectric. Other side, you know, here you created copper, and here we are going, it is the other face where we have not created anything. So select, make it in front of your eyes, and now again go to pick face, select, double click here, and here again second column of local WCS, align WCS with the select face. So now it is again aligned with the upside, it means dielectric material side. Here you are going to create another brick. This the third component we are creating, patch. It will be patch. Write this from minus PW, because this is the length of patch. We are naming it as a PL, sorry, minus PL by 2 to plus of PL by 2. If you're using capital, please use capital denotation only. If you're using lowercase, it means whatever you are denoting, the system should get the same variable value. V minimum, it should be minus PW by 2 to plus of PW by 2. And the thickness of this is same, 0 to MT. Copper annealed material was already selected last time for ground plane. So same material will be used for patch antenna also. Preview, it is asking for PL. Now here if you see, there is a link which we can see in the Google, you can find it. Here, we have a structure, it means based on the dielectric substrate, only the length and width of the patch depends. So with this, you can see for a microstrip antenna calculator, I opened it. It depends on this formula. Here you can see the width is derived from the dielectric constant and the frequency of resonance. And where epsilon r effective is what, depending on the epsilon r, because of the fringing field available in the width side, the actual length used to be different. And that's why epsilon r also used to be different. So it is a formula which you can see, which is depending on this, and length formula you can see it is depending and calculated using this. We require WH value. From this we can calculate the value of this. So in this structure, let me directly calculate. We have a dielectric constant of FR4 material which we use. If you open this FR4, you will find mentioned epsilon for R for dielectric, it means permittivity is 4.3, relative permittivity, and the height of this substrate is 1.5. we have taken SH, and the operating frequency is 2.4 gigahertz we are doing. So calculate this, you will find the result as 38.37 as a PW, it means width of the patch, and the length is 29.79. So with this, let me go to studio. 38.37 is the PW, and 29.79 in is our PL, it is patch length, and PW is 38.37. So with this, you can see a patch of metal is created. Preview it. Okay. So you can see now in the both side of the structure, one side I have a metal patch, another side I have, ground plane, and this side I have a metal patch. Is this clear to everyone? Now, if you see in the structure, you know this length from the center where this orientation is there. The length here is how much? It is PL. Total length is PL. So this from center, it is PL by 2 up to this yellow portion. And similarly, substrate, if we talk about, the total substrate length is SL. So it is SL by 2. If I want to know what is the distance, it means length of this. Okay, we want to create now strip line, the fourth component. So if the fourth component is we have to always create this patch strip line in the direction of W. So we can say direction perpendicular to W. This is W. So always strip line length will be this side. Strip, we have to transmission line, we have to connect it this way. So we have to connect, we have to make a strip line of same metallic strip line up to this length. So you can see that we need a up to this length as a brick here. Of this length, it will cover up completely. So we can say here width of this, here the width of this this is the length of, we can say, we will call this as fourth parameter, fourth component as a microstrip line. Microstrip line. Microstrip line, this line we want to create it. So for that, the brick will length will be ML, width will be MW, and MH will be thickness. Now you saw it is also metallic, so we want to make of the same thing. So MH is equal to MT. It means same metal thickness we want to create. Here MW we want to create, this is the width. MW will be 2.6. This width will be MW, width we want 2.6 mm, and ML is what? Now you can see if you divide this in the half, this is SL by 2 up to here, and this is PL by 2. So this length is remaining is what? SL by 2 minus PL by 2. So length is nothing but SL by 2 minus PL by 2. We are going to define this because already we have given PL and SL value. So for that, it will count the length. So let's do it in the CST Studio now. Here, you have to connect, you have to take another brick. But before do that, you know, the coordinate is lying here. So next step is first shift this coordinate from here to here. If you're able to see in the screen, you can see U is in this direction. Okay. And I have to shift this U from the center to this position. And how much is this distance? This distance is PL by 2. So I have to shift this WCS from here to up to this point. For doing this, near the WCS, one first point is there upside, you can see. It is transform WCS. This option, select it. And you know in which direction we want to shift now? That U should be shifted in the minus U direction, right? And how much it should be shifted? Minus U, it should be PL by 2 shifted. So we'll write in the U here minus PL by 2. Just preview and see what happens. So you can see our coordinate will shift from here to here. Press OK. Now we are ready to go for making a microstrip line. So here, what you're going to do, you are going to create another brick, take a brick, because now we shifted the coordinate from there to center to this. And here you're going to write it's a microstrip line, MSL. Writing it as what is the length of this brick which we want? You know, in the U direction here from U, we want from 0 to maximum. Maximum is going to be SL by 2 minus PL by 2. This is the length. SL by 2, the substrate half, minus PL half, the patch half is remaining 1, right? So we are going to write is from 0 to substrate SL by 2 half minus PL by 2 half, and this total value, what is coming, because we are doing in minus V direction, it should be minus. So we can say minus of SL by 2 minus PL by 2, that distance it should go in this direction. And what about the width? V is in the V direction, we have width of the strip line. And the width of the strip line, you are going to denote it as minus of MW by 2, exactly in the center from this point, positive and negative. So minus MW by 2 to plus of MW by 2. It will ask what is MW. We'll give at that time the value as 2.6. Width minimum is 0 to 2.6. Copper annealed. Preview it. So if you preview, it will show 2.6. We have to mention metal width 2.6. And here it is nothing but it's a strip line width. And here we are going to do OK. So you can see it has appeared here, this side of the same width. Okay. W direction is the width, which is metal thickness. We have wrongly written here MW. It should be MT, metal thickness. The thickness should be equal to the thickness of patch, which was MT, metal thickness, 0.03, which we have given. Yeah, this is the correct one. Okay. So with this, you can see we have created the strip line also now. Now rotate the structure and make convenient thickness of the metal available to you. We have done our four components which we have designed here. If you say, you can see this is the strip and this is the strip thickness. With this strip thickness here, you go to pick face and select only this thickness of the strip. Again, see, you can see in this structure, I am just zooming this strip portion towards us. So we can say this is the strip portion. I am going to zoom this portion. So I can see the metal thickness because I want to select it. So for this, pick face and select only this small yellow line cross section. So I've selected this. Now one step you have to do, you have to go to home, go to macros, because we are going to use the waveguide port for this, not the discrete port will work. So go to macros, solver, ports, and here calculate port extension. It will open up like this. Actually, when we connect, this, you can see in the screen here, this portion we have selected already. And now with this dimension, this is the strip line. So you can see here what we have given, the width of the strip line is 2.6, right? 2.6 mm. And the height of substrate is 1.5 already written. And the dielectric constant of our material is 4.3. Just put, because we have to take the factor up, because this is the thickness of substrate we have. To make it is a waveguide port, we have to get this extension factor here. K times H should be high. So what is K? Calculate here, just press calculate, 5.39. So we have to take the height of this port from here to upside as 5.39 times of this. Close it. Go to simulation, select waveguide port. So 5.31 is what, sorry, before to that, 5.31 was the extension factor. So just mention in your list here a new parameter which is K, and K is a coefficient which was 5.39 defined here. Before, without that it won't work, and we'll write it as a extension factor, waveguide extension factor. So waveguide extension factor we have selected. Now go to simulation and then go to waveguide port. Here in the waveguide port, when it is open, you remember that K value was coming. We have to write here K times SH. It means substrate thickness. So K was 5.39. We have already defined it. So I'm writing K star SH. SH is also defined already. So K star SH. Copy this for this Y minimum to this and Y maximum to 1.3 to this. So it will take from 1.3 afterwards upside. Here also copy it the same K times SH, and here you write as a SH only. With this preview, you will find an extension port available in the circuit. Here, extension port is previewed here, which is of the extra height of the width. Okay. Press OK. So we have extension port available now. Go to math solver. Here select normalize to fixed impedance. Apply, start. It will save the model, run the simulation. It will take some time to solve this because we are using student edition. So you can see the simulation is running because the structure is designed for some meshing. Let it complete the transmission transient analysis. Okay, so accept few warnings. My project is completely successful. Here you can see as parameters. As a 1D result for 2.44 gigahertz, we have defined it. We can shift it for the parameter because the values which we have taken approximate for this frequency. Energy, if you want to see the pattern display here for this 2D results, E field for 2.4 gigahertz. You can animate the result and can see the radiations appearing from a patch antenna. As it works as a ground plane, so you know it's a resonator cavity. When the upside and downside, it's working as a perfect electrical conducting walls from this, and the perfect magnetic walls from other side. So we can see the radiation patterns which is there. It is achieved at the resonant frequency, and the radiation occurs in the side because of the current distribution in the cavities wall. Yeah, a top on down metal structure. Other things also, like you can check it with the radiation pattern. Let me see the far field pattern at 2.4 gigahertz. One D results, if you see, you will find it. This is the radiation pattern. You can see actual pattern of this. We can calculate this directivity is around 90-degree. Angular lobe, side lobe, we can check it here as a result. So this is how we simulate a rectangular patch antenna. Now we what in this schematic we can do is the result which you have created. Go to the components. Here in the component, actually we have to make a inset width also. And for inset width, what we have to do, this was a patch structure which we created. But if you recall, this transmission line width which we have, why it was 2.6 taken, everything has a reason. Like here we have calculated it. You are the impedance calculator here. If you go for the strip line, you can search in Google this one, no issues. The formula for this micro strip line impedance calculator, if you go for, if you have a complete model schedule where if you put the value of trace width, height, it solves this equation for value of thickness of this metal strip, because we have upper side of this is a completely structure made up of air. So epsilon r is this is for the generalized strip line. It's a homogeneous strip line. So we can calculate using this formula, and this value comes for 2.6 around 50 ohm of resistance, and for that purpose, to keep it, we take the value of 2.6 as a strip line. So now in this structure we have to create a inset, because if you see here, a strip line, an extra, you can see this strip line up to here we created. We want to create this inset. It means this portion of metal need to be removed. This length is why not, and we want to remove this. Okay, we need to calculate the patch dimension, and we need to remove this for a length. What can be done for this? Go to your project, and here let me put in the front view, and here near the strip line we have to shift this coordinate from center to this side, to this position. So you know, actually this is v direction, this u direction, and the w is upside. So we want to shift this coordinate from here to this coordinate, we want to shift to this point. So for shifting this, what we can do, we can go to model, and here WCS upside first transform is there. In which direction we have to transform? We have to transform 0 to V position. It means that in the direction of V. And how much we want to shift? We want to shift it up to because 2.6 is the total length, right? So it is minus LL. It was W. Yeah, MW. MW was the total width was 2.6. So we have to go in the plus direction, MW by 2. So it will reach here. So in the V, if I change it here, MW by 2, let's see preview. Yes, it is shifting exactly to this point. And if I do it okay, my coordinate is settled at this point. Now create a brick here. And this brick will be called as an inset point. Okay. So we are creating one inset, and here U minimum in the U direction, we want to go up to inset we want. So take this inset as a 0 to this inset length. Inset length can be, we can calculate it. You can keep it as a 2.6 mm of inset, and V minimum, it is as general length. We can even calculate and find out how much is the transmission line inset length is required. We can increase it, and that V minimum from 0 to width of this, width of this we want this from minus MW by 2 of the same width. I want not MW. Okay, MW by 2 to plus MW by 2, or for example, certain, I'm taking a rough example here. Let's keep this width as length here as 7 mm, and for example here we want from 0 to 2.6, or we can say minus 1.3 to plus 1.3. It is same dimension I'm taking as a, and thickness of this is, let's write it as an MT, but U is there, so I will write minus MT, minus of MT. We are actually creating over this patch. Okay, so that's why it is important that we are writing as a plus of MT also. If we write, and if we select a material here as a vacuum, okay, let's preview what happens. So you can say inset is available here because I wrote it as a minus 0.3 to plus 0.3. It is not correct. Let me write 0 to 2.6 preview. Yeah, now exact perfect inset is available. Vacuum is selected. So it will ask me, what do you want to do this? It is asking cut away the portion. Yes, cut away the portion. Okay. So you can say one inset this created. Similarly, now transform this this coordinate from this position to a plus of, we want to transform this. So how much we want to do? MW. You can see from here to here in the V direct minus V direction, we want to shift it coordinate. So again, go to transform, move V. in the minus MW direction. So if we preview this, you can see it is coordinate is correctly moving. Press it OK. And again create the same dimension here, a brick here with it is inset 2. It doesn't matter whatever name we keep, because we are going to remove this content. And here this component is u minimum is what we kept there is 0 to 2.6. Sorry, length is we kept it 7. Same length we are keeping 0 to 7. Width is 0 to MW, it means 2.6. And the thickness is 0 to MT. Take vacuum here, preview. It is not coming correctly. Actually, yeah, it is minus V direction. So it will be minus of 2.6. Preview. Yes, it's correct. And here we do okay. It is asking cut away the portion. Now you can see our design has 2 inset point also. So with this, we have exactly patch which we created here. And with this structure, if we go to simulation, again waveguide port, setup solver, 50 ohm, start. So with the inset, actually, we have created an exact dimension of this structure. We can see with the microstrip length increase, we increase this length because, you know, strip line is now a longer time, not as a length of SL by 2 minus PL by 2, SL by 2 plus minus lambda by 2, but the line length we have increased here to provide a better impedance matching of this patch antenna, rectangular patch antenna. So this is if it is we want to create the inset. If it is a less thickness, you can take exact somewhere from example and you can create this structure. With this, I understand that everybody got this. Best wishes. Create this structure. Thank you very much.